What if we could literally mine the sky? Well, today we're diving into a breakthrough that does pretty much that. It's a way to turn carbon dioxide, our biggest climate villain, into a valuable resource for making fuels and plastics right out of thin air.
So let's start with this big question. What if we stopped thinking of CO2 as just waste? Imagine we could just pluck it right out of the atmosphere and turn it into something useful. It might sound like something out of a sci-fi movie, but a new breakthrough is making this a very, very real possibility.
So, how in the world does this work? Well, the whole idea really hangs on changing how we think about CO2. For decades, it's been the bad guy in the climate story, but this new approach reframes it completely. It's not trash to be buried, but a starting point of feedstock for a whole new kind of chemistry.
The secret sauce here is converting CO2 into something we actually need. And in this case, that something is methanol. Now, methanol is a huge deal. It's a foundational chemical building block. It's used to create everything from high-performance fuels to the plastics that are, well, all around us. The ultimate goal is to make these things from the carbon that's already in the air. Okay, so trying to convert CO2 isn't a totally new idea, but it's always been incredibly hard and super inefficient. The real problem, the bottleneck, has always been the catalysts, those special ingredients you need to get the chemical reactions started. They just haven't been up to the task. Right, so here's the deal. In the old school catalysts, the metal atoms that do all the heavy lifting are all jammed together in these messy little clumps. Think about it, like trying to cook in a kitchen where all your spoons and whisks are stuck together in one big metal ball. It's just not efficient, right? Only the atoms on the very surface of that clump can actually do any work. But this is where everything changes. Researchers at ETH Zurich have completely re-engineered the catalyst. They went back to the drawing board and completely solved that fundamental clumping problem. And this slide just lays it out perfectly. On the left, you've got the old way, messy, energy-hungry, and pretty wasteful. And on the right, the breakthrough. Instead of clumps, they figured out how to isolate every single metal atom. This means every atom is working, which lowers the energy needed and makes sure not a single bit of precious metal goes to waste. It's just smarter. Okay, check this out. This image shows us exactly what's going on at the atomic level. Each one of those little golden spheres is a single atom of a metal called indium. It's anchored to a surface, and it acts like its own tiny microscopic factory, grabbing CO2 molecules and turning them into methanol. It's amazing. So the whole thing can really be broken down into three pretty simple steps. First, you introduce carbon dioxide and hydrogen to the catalyst surface. Then those individual indium atoms get to work and, do their magic. And finally, just like that, you get your valuable end product, methanol, created with incredible efficiency.
So a new catalyst is great news if you're a chemist, for sure. But what does it mean for the rest of us, for the real world? Well, the implications here are actually huge. The benefits just start stacking up one after another. Because every single atom is working at full capacity, the whole process is way faster. And because it's so efficient, it needs a lot less energy. It's also cleaner, producing less unwanted chemical waste. Plus, scientists have way more control over the reaction and they get the absolute most out of the precious metals they use. It's a win-win-win. But here it is. This is the real game changer. The source material points out that if the hydrogen and the energy needed to power this whole process come from renewable sources, like wind or solar, then the entire production of methanol can become climatically neutral. Think about that. We could be creating fuels and plastics from the air without adding any new carbon to the atmosphere. Of course, this all sounds fantastic in a nice, clean lab, but the big question is always the same. Can it survive out there, in the harsh, messy environment of a real industrial plant? And the answer is a big, resounding yes. This single number tells you almost everything you need to know. 300 degrees Celsius. That's how hot it can get while this catalyst stays stable and active, and that is a critical benchmark for surviving in the real world of industrial production. Yeah, this is not some fragile lab experiment. The way those indium atoms are locked into place makes the whole catalyst incredibly tough. It can handle not just those high temperatures, but also the intense pressures that are common in large-scale production. This thing is built to last. And that really brings us to our final thought. This is about more than just one cool catalyst. It's about proving that something we've always considered waste can actually be an incredibly valuable resource.
It forces us to ask a much bigger question. If we can now literally mine the sky for fuel, what other impossibilities are we going to tackle next?